Hello and welcome to 7.5 binomial distribution. All right. Up until this point, we've been so far these last two sections we've been talking about how to gather data, right? Not super exciting. And then before that we talked about like population versus sample, right? Now we're going to kind of go back to what do you do when you have data, right? We in that very first section, 7.3, we were talking about is it really accurate? Right? Is the data really accurate? Well, we're going to talk about that again in 7.6, but we've only kind of dealt with one type of data set, right? We've only really calculated stuff for one type of data set. In 7.3, we're looking for mean and we're looking for standard deviation. Basically, the only question we asked was, what's the average number of ... We've never really asked another type of question. But then in the other half of 7.3, we saw that there was a question of percent. What do you do when the question's not, what's the average? Well, then we have a different type of distribution. It's called binomial. Okay, these are our yes or no questions. The classic example is voting, right? Who do you vote for? Blank percent votes for this person, blank percent votes for that person. That's not an average. Okay, the average number of people is a question, but that's not going to tell us about favorites in a voting. It's not going to have another example. Do you like cats? That's not really going to be answered with an average number, right? I mean, you could do an average number of people who likes cats, but that's not like you're forcing that, right? So there is another type of question, a yes or no question. Yes or no, two answers, binomial. And there's where we have binomial coming up, okay? Couple of things we can use to kind of deal with binomial situations. The first part is called combinations. We really kind of need to think about all the different ways we can organize stuff before we can talk about how to organize it into percents. So for example, you got Carly. She has 6 different types of posters for 6 different bands, and she wants to hang them up on the wall. Okay, there are a bunch of different ways she could do that. There are not 6 ways she could hang that up on the wall. Okay, but there are 6 spots. 1, 2, 3, 4, 5, 6. Right? This is gonna sound a throwback to last year, by the way. She has 6 options here. As soon as she puts one up, though, she only has 5 options here, and 4 options there, and 3 options there, and 2 options there, 1 option there. You see how it kind of goes down? Once she's used a poster, she can't use it again. And so what we get is what we call factorial, right? We have a factorial, and it goes down. It's actually a little bit even more than that. Once she puts 1 up, does it matter if she puts them in the same order, right, or not? Because if she chooses combination 1, 2, 3, 4, 5, 6, isn't that the same combination as 1, 2, or is that the same combination as 1, 2, 3, 4, 6, 5? Sometimes the answer is yes, sometimes it's no. If I'm choosing people for a team, the answer is yes. In Carly's case, the answer is no, right? If I'm in these posters putting 5 before 6, not the same thing. But choosing Johnny first versus Sally first when we're all going to be on the same team, it doesn't really matter, right? And so we get kind of this combination versus permutation. Down on the next page, you're going to see a formula for combination. It's going to make your skin crawl. Just go ahead and box it. It's not as bad as you think, all right? What it is, that little exclamation point, we're not just super excited about math. It is a factorial. So in Carly's situation, when we had 6, 5, 4, 3, 2, 1, that is the same thing as 6 factorial. 6, 5, 4, 3, 2, 1 is the same thing as 6 factorial. Now your factorial can be found under PRB. Okay, there's a button on the TI-30. PRB, probability. Okay, and it looks like factorial. Okay, cool. We kind of already talked a little bit binomial distribution. I shouldn't be super unfamiliar with factorial, but it's there. Alrighty, now how does this help us? First off, a combination is also written like this. Okay, you get 2 parentheses. If we look at this formula, it's N choose R is how we see that. So if I wanted to choose 6 from 12, or I wanted to choose 4 from 12 things, then I would say it's 12 choose 4. I'm sorry, 12 choose 6, whatever I said. We're going to see a bunch of these, so you get to kind of mess around with it. And then it plugs into this formula. It is also written this way n choose r. Okay, and that's how we're going to use it for binomial distribution. So every time we see this n choose r format, this one over here, I'm also going to write it this way so that we get used to it. Okay, it's just the same idea. And then we're going to have another formula. So let's just jump down to some choosing problems. Okay, exercise 1 here. Lots of information, good information everywhere. Flip on over. Alrighty, 9 factorial over 8 factorial. So what the heck does that mean? I'm going to show you kind of a quick way to make this a little easier. Okay, we gotta show some work. 19 factorial would be 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Yeah, okay. So that's all 19 factorial. That is now being divided by 8 factorial. 8, 7, 6, 5, 4, 3, 2, 1. And notice those are all being multiplied. Here's the thing though. Look at the top and the bottom there. There's a reason I wrote this at the end. Yeah, that's going to cancel, 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 that's going to cancel. So we get a lot of crap canceling, and we're just left with these top 10 numbers. Therefore, we can just do that part. 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10. And our answer is very large. 3.35 times 10 to the 11th. Okay, it's a very large number. Obviously, this number is super big, and so we're going to round it. But this canceling idea is going to come up a lot in combinatorics, okay? In combinations. Okay, so let's do another combo problem now. We've got this idea that we have 9 choose 5. If that part didn't make sense to you, you're going to see it like 8 cents more times today. 9 choose 5, so otherwise known as 9 choose 5. Okay. This means I have 9 things. I want to choose 5 from them. How many ways can I do that? I could sit here and I could have the 5 little spots and I could come up with all the different combinations, but instead I think I'm just going to plug this into the formula. 9 factorial over 9 minus 5 factorial times 5 factorial. That's actually going to be the number of combinations. Maybe let's clean this up a little bit. 9 factorial over 4 factorial, 5 factorial. Yeah, okay. I just did 9 minus 5. Well, 9 would be 9, 8, 7, 6, 5, 4, 3, 2, 1, all being multiplied. 4 would be 4, 3, 2, 1. And 5 would be 5, 4, 3, 2, 1. So we see this 5 is going to cancel with that 5 all the way down to 1. That's kind of what we wanted to have happen, because now we can just do the first half. We can do 9 times 8 times 7 times 6 over 4 times 3 times 2 times 1. 9 times 8 times 7 times 6 divided by, now be careful, you want to put the denominator into parentheses in your calculator. You may even want to do both. Come on, here we go. But then if we divide by 4 times 3 times 2, times it by 1 is a waste of time, we get 126. All right, we get 126 ways to take 9 things and put them into 5 spots. Sweet. Go ahead and try 14 choose 3, aka 14 choose 3, right? Try those out. See how many combinations there are to take, how many ways there are to take 14 things and put them into 3 spots. All right, I hope you had some time to try that. If you didn't, take like 30 more seconds max, because we have a lot to talk about today. But if you did that, you should have gotten 364. 364 ways to put 3 things into 14, no, 3 things into 14, no. To choose 3 things from 14. There we go. Okay, why the crap are we doing this? This is totally left wing. What are you talking about, Ms. K? Why are we looking at ways to organize things? You were just talking about statistics and yes or no questions. Like, how does this relate? This relates because if I were to take a percent, so we're going to look at binomial distribution now. Another formula we have is this guy. Okay, go ahead and box that guy. Do you see how that n choose x is in there? We need to know about that before we can start doing these probabilities. So it's back on page 19. You have, like, it doesn't really make sense as to what it's talking about right now, but this is what we call the binomial distribution formula, okay? It's very similar to our z-score formula from way back when. It's going to help us find a certain probability. We don't have to draw a normal curve for this one. There's actually not really a binomial curve. I mean, there's one, but it's really weird. We're just going to use this guy. It's going to make the most sense when we deal with a problem. So let's just go dive into a problem. Let's go dive into example 4. A girls' dance class performance contains a scene involving a group of 6 dancers. There are 11 dancers. Oh, this is just a choose problem. My bad. We're going to skip number 4 for a second. We'll come back to number 4. Each year, a company selects a number of employees for a management training program given by a nearby university. On average, 65% of those sent into training program complete the program. Okay, so we actually have some data here. We have 65%. If 7 people are sent by the company, what is the probability that exactly 5 will complete the program? Interesting. Okay, so we have this scenario where we already know something. We know that 65% complete this program. Yes, they've completed it. No, they haven't. Notice the binomialness of that question, right? Do they actually complete it? Yes or no. It's not, well, they completed in the average time of, no. 65% of people did it. Okay? We already know this. We already know that that's the percent that finished. So now we want to build on that question. If 7 people go, what's the probability that 5 will do that? Right? 65% is everybody, but what's the probability that we're going to get 5 out of 7? Right? Kind of think like a dice game. Here's where that formula comes in. Let's go back to that formula now. This capital P is not the same thing as that lowercase p. The capital P is the probability. So that is what we're after. We are after that probability that this is going to happen. Then we have, we'll just copy down right here, n choose x. Okay, so some choosing of things. That's probably going to come from our 7 choose 5. Interesting. Okay. The P here is the probability we already have, the percent we already have. So that's going to be our 65. That x is going to go up here to the number of people we actually want this to happen to. Q is going to be the flip side of this, okay? It's going to be the other side of the coin. Q is going to be the people that are not doing this, the people who have failed, okay? These are the failures. That sounds really bad, but to fail a test doesn't necessarily mean a bad thing. You could fail a test about having diabetes, and that would be a great thing if you didn't have diabetes, right? So these are what we call our failures. The Q in this case would be 100 minus those 65%, or 35% of people who do not complete this program. And as you guessed it, the power on that is also going to be the flip side. It's going to be n minus x, or the 2 people we don't want to pass this program. So let's go back and plug all that in now. For this scenario, it would be 7 people, choose 5 of them to actually finish. We're going to have that 0.65 who could actually pull it off to the number of people we want to pull it off, right? We want them to actually get through. And then on the flip side, the 35% who don't, to the 7 minus 5, aka the 2 people we don't want, right? All right, let's have our calculator help us with that. Calculator, my friend, is there any way you could do choose for me a little faster? There is. Thank you, calculator. Go ahead and press that PRB button again, the probability button. Right under factorial, you should see n choose r. Weird. That symbol looks familiar, right? Oh my gosh, look at that. It's going to do that part for us. So we just got to make sure, we got to back out of it, got to choose, you got to select 7, then the n choose r button, and then the 5. It's going to spit out 7. Oops. Make sure you don't use NPR. That's a different thing. Use n choose r 5. It's going to spit out 21. Cool beans, bro. 21 times 0.65 to the 5th times 0.35 to the 2nd. We get 0.298. In other words, 29.8%. There's only a 29.8% chance that we will have 5 of the 7 finish when only about 65% can do it anyway. All right, that's a classic example of binomial distribution. We're going to try this out a couple more times. We've got lots of different examples here, but right now I want you to go back and finish 4. Do 4. 4 is just a combinations problem. I want you to do it really fast. A girls' dance class performance contains a scene involving a group of 6 dancers. There are 11 dancers in the class who can perform this routine. How many different groups of 6 can be performed if there are from these 11 dancers? What is even that question? How many different groups of 6 can come out of this 11? Oh, that's 11 choose 6. Type out real fast. What do you get? 462. Different groups. So much faster, right? Showing the calculations with the formula, yes, you may see that being asked on a test. Okay, so don't panic over it, but it is something that you kind of need to know why this thing's working, what's it spitting out. But really, at this point in the day, we worry more about this. Okay, what are we doing with probability? Alrighty, ask questions as you have them, but try not to stop, right? Because we don't want this video to go too long, so hold your questions for the end. If you have questions on the actual, combination button and finding that, you can ask your neighbor, but don't lose anything from these next 2 examples. All right, number 6. A study shows that 6% of American teenagers have tattoos. We hope that's 6% over 18. If 9 teenagers are randomly selected, what is the probability that exactly 2 of them will have a tattoo? So we already know that 6% of the teenagers have tattoos. But now what's the probability that if I choose 9, 2 will be there that actually has them? So let's use our formula. So probability, let's see, 9 choose 2, right? That's the combination in question. 6%, careful, 0.06 to the 2 that we want to happen, times what's the opposite of that? That would be 100 minus 6, which is 94, to the 9 minus 2, or 7. Right, we want 9 minus 2, and that way we get the other 7 who don't. Right, we kind of have to keep those guys in because they are just as vital to this population or to this probability as the people who succeed do. Okay, all right. Let's type that all in now. 9 NCR 2 gives us 36 times the 0.06 to the second. The 0.94 to the 7th, times that all out now. A whopping 0.084 or 8.4%. That makes sense, seeing as how only 6% of all the teenagers anyway have tattoos. Now on top of that, if you had tried to pick more from that, we get 8.4. The probability does go a little bit up. That's an interesting side tidbit, but it's based off the fact that you've chosen only 9. Right? Small sample sizes give you different probabilities. Alrighty, last one. Assume that 13% of people are left-handed. Okay, pretty cool. If we select 5 people at random, find the probability of each outcome described below. There are exactly 2 lefties in the group. Okay, so question number 1, exactly 2 lefties. How does that differ from question number 2? There are at most 2 lefties in the group. Interesting. Okay, almost the same question. We're going to have to deal with that. But let's start with part A. Exactly 2 lefties. I recommend we do have some time, so pause the video, try out, see if you can figure out part A on your own. All right, hopefully you pause the video. If not, go ahead and do that. Just don't take too much time, okay? All right, so probability would be of the 5 people, choose 2, 0.13% to the 2 we want to succeed, times, let's see, 100 minus 13 is 87, to the 3 people we don't want to succeed, right? And those 2 numbers should definitely always add to the total number of people you're choosing from. If they don't, that's a big problem. All right, we punch that all in the calculator. 5 choose 2, we get 10 times the 0.13 to the second times the 0.87 to the third. Ooh, a whopping 11 sorry, my calculator glitched out on me. 1%. 11.1%. Woot woot. Whoop-de-doo. All right. Hopefully that one wasn't too bad. Now we got to deal with at most 2. Well, that's a few more people, huh? Because we could have 2, we could have 1, or we could have 0. Our formula isn't exactly like z-score. It's not looking at less than. It's looking at only. Okay, so this is only 2. This is exactly 2. We already know exactly 2, so we can kind of bring that over. What about our other options, though? Our other options were 1 or 0. We're going to have to calculate those as well. All right, we can do this. We can do this. To calculate 1, we need 5 choose 1, 13% to the first, and the 87% to the other 4. Then we also need 0. 5 choose 0. Well, that's easy. There's only one way to choose 0. Times 0.13 to the 0. Oh, wait. That's just 1, 2. So 1, 1. And 0.87 to the 5th. That one I don't know off the top of my head. All right, so it looks like at least for 0, not too bad. We have 0.49. Oh, let's just put it in percent. 49.8%. For the second one, though, let's see, how many ways to choose one thing from 5? That would be 5 ways, but my calculator will also tell me that. So 5 times 0.13 to the first times 0.87 to the fourth. We get 37.2%. And then, well, okay, so and then we've got all 3 of our scenarios. So I just used the formula 3 times, right, for the 3 possibilities that represent at most 2. But now how do I use them to find the probability? Oh, I got to add them all up. All right, we add them all up, and we'll find the total probability, right? Because the word total means add them all up. So 11.1 plus 37.2 times 49.8. Whoa. Not times, sorry, 11.1 plus 37.2 plus 49.8, we get 98.1. It is actually 98.1%, at most of them will be 2. Why is that the case? Well, really because only 13% of people are left-handed. Trying to get higher than that is incredibly difficult. Trying to get 4 out of 5 to be left-handed when not even half the country is left-handed, incredibly improbable. So the lower numbers, yeah, that makes sense. Alrighty, so now we can see kind of how binomial distribution works. If we did want to find at least 2, we could do the same thing. We could do 2, 3, 4, 5, right? Or we could take the flip side of at most 2, right? So if I wanted to find at least 1, well, then the only person who doesn't fall in that category is 0. So I would just take out 0. And it would be 100 minus that 49.8. So it's the same idea as z-score. With what you want, this formula only gives us exactly. So if I wanted something else, I'd have to maneuver it around to find those pieces, okay? And it's going to take some practice, right? It's going to take some practice. Binomial distribution is definitely not easy. We're going to practice with it a little bit more and then head over to 7.6. But I will see you there tomorrow.